let's move on to the next one. This looks like a conditional statement, which I guess is okay. So you have the in-center of ABC. You do it like this. So, we want to see where it meets the sides. Okay, so let's just do this for now. Eventually, we're going to draw ABC, so I'll just draw it right now. And we're going to have to relabel some stuff, but we'll get there. So we have this and this. And they meet the sides at D, E, and F. So D we do end up drawing. So I'm going to rename these points. And I call it X, Y, and Z. Z. Now they should automatically be labeled D and F, hopefully. So we have P, E, and let me try to get F. There we go. So we want to draw EF and see where it meets the circle at L and T. F is on segment LE, that's good. And M is the midpoint of BC. So that's M. Show that if DT is tangent to the incircle, then IL bisects MLT. It's a very random statement, but let's see what we can do with it. Okay, so you want this to be tangent. I just don't want F and Z to be so close together, but maybe it has to be. So something like that. So yeah, if they're tangent, I mean, if that's true, then there would be some point such that like dx equals dg. So yeah, I could draw the midpoints of the arcs. I don't know if it's worth it. So MLT, let's think about that. I wonder if in that case MG and L would be collinear. Let's see. I draw the angle bisector. So yeah, that looks like it passed through I. But I'm not sure if this would ML would pass through point G. Maybe it does though. So it's hard to tell. Yeah, I think the diagram is close at least. Yeah, it's got a pretty simple statement. Is there a way to draw it exact? Don't know. So now I'm thinking about like Poncelet's porism. How we could construct an exact figure of this diagram. Yeah, IL bisects MLT. Let's think about what that means. Maybe I is the incenter of another triangle of but yeah, it's a very random condition. Let's see how close my diagram is. It's pretty close. I mean, it's not exact, but there we go.
Can you draw the diameter of I from X?
Okay.
Yeah, I just like feel like T X prime is tangent.
Yeah.
I don't know if that's true.
Let's see. It looks true. Yeah,
I mean, it's close. Yeah.
that's interesting. So yeah, maybe I could try to draw an exact diagram that way, if we think that that's true. Basically, I'd start. Well, actually, I'm not sure. Yeah, that's a good observation. Should we use the angle bisector theorem? How should we do this? Pretty interesting diagram. So yeah, it's like you take the topmost point and then you draw the tangent. So yeah, I mean, in that case, maybe it's worth trying. Oh, interesting. So it looks like these would be collinear then. Okay. Yeah, like we know bx equals ck. But it's interesting. Okay, so what are we saying? We're saying LM and AX prime, or LM and AK would meet in the circle in that situation.
Okay, I want to share some of my progress.
Okay.
So we want, okay, firstly, I can show this, and it is not too hard, just a bit of projective geometry, that LTMD is cyclic.
Okay.
And this doesn't even use the condition. So like, you don't need the condition that dt is tangent for this part.
Okay.
So we then have that angle MLT is just MDT. And
yeah.
if we use the condition, then this, so we want half MDT, and then you like take 180 minus MDT and you get XDT, and then we take the half, you actually just get XDA, because XDA is DTA, TDA.
XDA is TDA, yeah, and that would be C plus A over 2.
Yeah, but I think this isn't the optimal way we can kind of see that angle.
Okay.
This is okay. So we want to show that TLI is that angle, 90 minus XDA.
Yeah.
And 90 minus XDA is actually just XID. And this is also AI X prime.
Yes.
And I'm kind of assuming that TX prime is tangent. And it looks true, and I'm kind of trying to solve the problem assuming that.
Yeah.
And then we can try showing that TX prime is tangent. Okay, and if you took the intersections of IX and AD and those two with EF, so intersection of xi with df and yeah, those two. Then by those angles, we would need to show that ni is tangent to LPI.
Okay.
Okay. And another thing which I found, and I'm not sure why this is true, is that x prime ti seems to be equal to, so the angle x prime ti,
Yeah.
it is equal to ILN.
ILN.
Basically, ix prime t is tangent to AI.
Okay. So let me draw IT. So you're saying this angle equals this angle.
Yes. So 0.01 difference, I think that is true.
Yeah, yeah.
And also looks like those two angles are also equal to ITD.
Okay. So this would be bisect this angle also. Okay.
Yeah. Just let me think a bit. Maybe we have that ITD is ILP. Okay, so TX prime is parallel to BC, let's say that.
Mm-hmm.
Then X prime TD is equal to
EDC.
yeah, CDT.
Mm-hmm.
And when you take half of it, you just get that angle we were talking about.
Yeah.
And so, yeah, but we don't know it is equal to ILP, but we at least know that those two angles at T are the same and they are equal to that angle we are trying to get, kind of.
Yeah, ILP.
And yeah, and also then we have that triangles IDT and X prime IT are similar.
IDT and X prime IT.
Yes. Because
Because they are both right triangles and they have angle.
not I don't think we directly have that they are right. But yeah, actually we can just angle trace they're both right triangles, yeah.
Well, so IX prime T we would know is right if this is tangent, but BIT, how would we know that that's right?
If you look at the angle at D and the angle at T,
Mm-hmm.
so D is 90 minus
Oh yeah,
90 minus, yeah.
it's the same. It's the same as ADB, and then yeah, you can chase that.
Yeah. Okay. I think that's it.
Okay. So I wonder. A lot of interesting observations. Yeah, MLT is just MBT. And then we want to find ILT, like you mentioned. But yeah, we have to use some where the E and F are the feet of the angle bisectors, right? We use that?
We didn't use that, but you were kind of angle tracing the easy stuff.
Well, I guess that's used in proving MDLT is cyclic, right?
Yeah, actually, yes.
So yeah.
But only in that part.
Yeah. So basically, if we had three, I mean, yeah, I wonder if maybe that is enough just to use it that way, but I don't know. We want to show that ILT. Yes, if we can show that, that would solve it. Well,
Not really, but we would need to show T X prime is also parallel.
is parallel. Yeah.
Yeah.
So yeah, that wouldn't solve it totally. With point M and like think about that. Yeah, I feel like it might be easier to work with ILM than ILT. I don't know. I'm trying to think how we would show that AK and ML are concur on the circle. I wonder if, actually, never mind. Where if this point I guess another way to say it is that the circumcircles of LIG and TIG are the same size. Is that right? Doesn't look maybe TIGM is cyclic. That looks true. Although it could just be very close to being cyclic. But let's think about that. I'm confused. Wait, so we have CMT. Oh, because that's not 180 minus it. That's why.
I have a couple of ideas.
Okay.
We want to show that x prime ti is ILT.
Yes.
So we can extend Li and Ti to meet VC.
Okay.
And then we would want to show that we have a cyclic quadrilateral.
All right.
And as I've checked, this quadrilateral is cyclic even when the condition is not there.
Okay. So this.
Yes.
Okay.
And also, looks like A is the center of spiral similarity, which takes L and LT to QR.
Okay.
And like when you intersect QL and TR, they would then intersect on the circle. But that point looks like the midpoint of the arc.
Yes. Okay. Interesting.
So if we could show this, then the only thing left would be to show that Tx prime is actually tangent.
All right, so let me understand this. So angle TLI is TLR, and angle the angle we want to show is equal to, so x prime ti, that would be TQR. So yeah. So if we could show that this is cyclic, and you said that's true independent of what?
Of the arbitrary condition that dt
It's
is
tangent.
tangent. Yeah.
That's true regardless. So basically, so if you just take wherever EF meets the circle, and even if it's not tangent, that's still cyclic, is what you're saying.
Yes.
Okay.
And that is really beautiful to me.
Yeah. So yeah, if that's true, you would think it wouldn't be that hard to show. So let's see. Interesting. So EF meets the circle at T and L, and then you let TI and LI intersect it at Q and R, and you want to show that that's cyclic. So, yeah, if they intersected on the circle, if they intersected at S, like, do you know if S is always the midpoint, regardless of the tangency condition? Looks like it.
Yeah, looks like it.
Okay. So maybe, let's see. I wonder if we can use power of points somehow. So like, no, maybe we could somehow show QLM QLMU is cyclic. That would be the same as, yeah, let's say we didn't know those are, well, yeah, it's kind of just equivalent. Maybe we should also draw this. So I just broke my pen. Yeah, we want to show this tangency equivalent is tangency condition is equivalent to Tx prime being tangent. Yeah, I haven't seen anything like this before. Well, yeah, but it looks interesting. QL and S are collinear. Once we know that, it proves that QLTR is cyclic, because then QLMU would be cyclic by right angles. And so by power of a point, we'd show that this is cyclic. So yeah, showing that QL and S are collinear is enough. Well, we also have to show Tx prime is tangent after that, but it's a cool configuration. Let's see, we have, so all three of these circles would have the same radical axis, right? So yeah, I don't know if we can use the power ratio lemma or something. So actually, that is an interesting idea. So what if we try to use the power ratio lemma? So we would want to show, so we'd have QB times QC over QD times QM, and we want to show it's the same with point R. I like the idea, but I'm not sure if it's that easy. I wonder if let's say maybe QT is perpendicular to AU. And then all those points would lie in a circle. All right, let's spend a couple more minutes and then we can move on to the next problem. I think, so yeah, I mean, even if we show this is cyclic, there would still be some work to show that this is tangent. So yeah, I don't think it'll be that easy to finish it.
I think we did a lot of progress.
Okay. So let's try something different. So this one looks not too bad. Let's see. So we have a triangle ABC. So we want ABC to be less than ACB. Okay. We have the perpendicular from, okay, so we draw the circumcircle. And we draw the perpendicular from A to BC. We see where it meets the circumcircle. So that's like the reflection of the orthocenter over BC. Right? I like that better. This would be D, M is the midpoint of AD. Whoops. That would be M. Maybe it's worth drawing the center of the circle O. So that way OM would be perpendicular. The tangent at A hits the perpendicular bisector of AD, which would be OM. At E, and the circumcircle of MDE hits the circumcircle of ABC at F. That's it. And this is F. And then G is the perpendicular from A to BD. And N is the midpoint of AG. I think I have an altitude tool. Yes. N is the midpoint. So we want to show that B, N, and F are 20. Interesting. Whoops. Don't want to do that. O lie on that. Looks like it does. So, oh, not necessarily. Okay.
I think we can draw the parallel from B to AG to make the circle.
From B to AG. Okay.
Yeah, the parallel.
And basically draw this point.
Yeah.
Right.
So maybe you want to prove that AHDF is harmonic. This may solve the problem.
Okay. Oh yeah, because by symmetry, this is also tangent, right? So that would be the same as saying HF and E are collinear. Yeah, if AE is tangent, then DE has to be tangent. Okay. So let's try to show that's harmonic. It's the same as showing HF as a median. And I wonder if we can angle chase that. Well, actually, I think that is true, obviously, because we know angle HFD is 90 degrees because HAD is 90, and we also know that DFE is 90. So basically, HF and E are collinear. And so then, by definition of harmonic, HAFD has to be harmonic.
Yeah, so like we're basically done.
Or what? How does that finish it?
So you get that AG and so you get that BH, BA, BN, BG is, let's say is harmonic because BH is parallel to AG. And then you also have that HAFD is harmonic. So you project to B, imply that BNF is collinear.
Okay. Project through B. So HAFD is harmonic, and we're projecting through B onto AG. So it's really that simple. Yeah. Okay. Yeah, that's too easy. Yeah, some of them are really easy. So, so we have HFD. Just type it up quickly. So 90 HFD per and then that's equal to angle DME. DFE. So that means that HF and E are collinear. I'm going to want to put up top by symmetry, since EA is tangent, ED is tangent. So and then so this implies that HAFD is harmonic. And then we project those 4 points through B. Oh, but first I should define what H is, because it wasn't even defined in the problem statement. So you said let H be the antipode of D. Yeah, creating that point was key. Once you do that, it kind of falls apart. Projecting through, well, so then BH is going to be parallel to AG. And projecting through B onto AD, onto HE, I mean. Thinking about the best way to say this. So it would be like AG something like this. Maybe I don't have it exactly right, but it's the basic idea. So and that means that B, F, and N are collinear. Or B. All right, let's move on to the next problem. Okay. Nice. There we go. So that other one looked like it might be a little harder. This one. Let's see. H is the orthocenter. And we see where they meet the circumcircle. So those are going to be the reflections over the sides. We're going to rename a couple things. Cheat and just reflect it. We get this and this. And this will be D. And this, whoops. D. This will be E. And why is this not working? E. All these X and Y or something. And E is on a B. P is any point between B and the F. Let's call this P. And then PH intersects AC at Q. Interesting. So a lot of options for where to put P. And this would be Q. And then AEP, it hits CH at S. And ADQ, it's BH at R. And the two circumcircles meet at J. let's and it looks like they intersect on PQ, so maybe that's not hard to show. But they intersect at J, which looks like it lies on the line PQ. And we want to show that RS is the perpendicular bisector of HJ. Is that true? Yes. And I wonder if A also lies on that. So maybe 2016 is easier than other years. I don't know. But let's see. So it looks like A, R, and S are collinear, and they're all on the perpendicular bisector. That's what it looks like. So first of all, can we show that these circles intersect on PQ? So this is a kite. Basically, we have two kites, right? We know this is a kite, APH, and we know ADQH is a kite. Is that enough to show these circles intersect on PQ? I think it is, because angle AJP is 180 minus AEP, which is 180 minus AHP, which is AHQ. Let me think about that again. I think it's just an angle chase, right? AJP is 180 minus AEP, which is 180 minus AHP. And we want to show that, which is AHQ. So is that true? AJ equals AH? I think I just proved that. Yeah, it looks like there's a circle through A passing through all those points. And from there, like I would think it has to be not that hard to show that these intersect on PQ. Because AJQ is 180 minus ADQ. Feels like it should be easy. I know that's not a good argument, but yeah, it is true, because AJP is 180 minus AEP, and AJQ is 180 minus ADQ. But if you reflect ADQ over AQ, you get AHQ, and if you reflect AEP over AB, you get AHP, and those out of 180. So yeah, so these concur on PQ. And then this circle exists. So we have a lot of information. Yeah, so A lies on the perpendicular bisector of HJ because this circle exists. So I proved that AHJ is isosceles. And then probably by an angle chase, maybe I could show that AR is perpendicular to PQ. it's the same as saying AR is perpendicular to QJ. Which would mean that this angle plus this angle is 90. Which would mean that this angle. Okay, so that's also true. By an angle chase. So I know that AR is perpendicular to HJ. And then by the same argument, AS is perpendicular. Okay, so I just solved it. Yeah, so this is an easy problem. Yes. I don't even know if I should write it up. I'll write it up quickly. But, so I'll say triangle AEP. So E and H are reflections over AB. And D and H are reflections over AC. And then basically, so AHP plus AHQ equals 180. So here's so for now, I'm going to show that these circles concur on PQ. So if this is true, then AEP plus ABQ equals 180. If that's true, then then 180 minus this plus 180 minus that also has to equal 180. So let me put these on new lines. Right, that would mean that that's true. And that means that angle AJP plus angle AJQ equals 180. And that implies those circles concur on, what is it, AEP and ADQ? Concur on, I think it's PQ, right? Yeah. Okay. And then once we know that, an angle chase shows that angle AJH is AHJ. So therefore, so first I'll actually just write this. So, I mean, this by itself means that AE equals AH equals AQ equals AB. And then, so we have angle AJ. So angle AJH is ADQ is AHQ. That implies that, I mean, AJ equals AE. So that means that JEHQD cyclic with center A. I didn't put the points in the right order, but it's okay. Q is not on, just JEHD. I think I got to get rid of AQ here and here. And once we have this, so A lies on the bisector of HJ. And then I'll show that R lies on it, and then the same argument shows that S lies on it. So RS is the perpendicular bisector. So I'm going to show that angle RAQ plus AQH is 90. So angle RAQ is RDQ, which is DHQ. So that is 90 minus AQH. And that implies that AR is perpendicular to HJ. And then similarly, AS is perpendicular to HJ. So both of those together imply RS is the bisector of HJ. All right. So some problems are easy. Let's see how much time we have left. Half hour. So we could go back to this one if you guys want. Or so yeah, we have a couple options. We can go back to this one. We could try to figure out this. I don't think that sounds too fun. Or we could go look up another problem.
I would rather continue this one since I've been doing it while you were doing the last two problems.
Oh, okay. Sounds good.
I think I'm close to showing that Tx prime is parallel.
Oh, yeah?
So what I was thinking doing is extend Tx prime and Td to meet the circle.
Okay.
And use the Poncelet-Poisson.
Ah, that's interesting. All right. So we have this and this, E and W.
And yeah, I'm not sure exactly how to prove this, but it looks like something kind of well known, to be honest.
Okay.
So we can see that the line WT, it is just the reflection of BC in the angle bisector.
BC in AI?
Yeah.
Okay. Yeah, because D and X are tangent. Yeah. Or DX and DG are tangent.
Yeah, because of the tangency.
Yeah.
And then V should be the Sharky Devil point. That is something I just checked that it works, but like it must be well known.
Yeah.
So like reflect the BC and then take the point which with the Poncelet-Poisson and you get Sharky Devil point. I think that is something we can prove if we try to.
Yeah.
And yeah. And then I think that triangles VAI and IX prime T are similar.
Okay. VAI and IX prime T?
Yeah, I think they are similar. We can check actually.
Yeah, I can check that.
No, they're not actually. Oh.
Okay.
Okay, maybe then that just doesn't work.
But it is interesting that the Sharkey double point is like, when you connect it to x prime, it's parallel.
Well, that's not true in general, but
But for this case, yeah.
yes.
Interesting. One sec, I'll be right back. All right, and back. Yeah, I feel like once you solve this problem, there's probably a way to construct the diagram exactly. I'm just going to keep trying to show that this is cyclic for the time being. Or that these are collinear. Q, L, S.
Also, what I noticed is that W is under the problem condition the touch point of mixed linear incircle.
The moment you said you noticed W, before you even said it, I guessed it would be mixed linear.
Oh.
That's funny. Yeah. And yeah, that would make sense if VT is parallel, because then S is the midpoint of VT, so WI has to be like the bisector. Or WI would be the bisector. Or Q looks like Q, W and U might be collinear also. Maybe even AV and Q are collinear. Yeah, so a lot going on here. So yeah, I mean, like we know a lot about point Q and the Sharkey double configuration, right? This is cyclic, it's tangent to AU.
We actually know that BCVW is harmonic.
BCVW?
BCVW.
Hmm.
that you can get just by projection from T.
Okay, so you project through T
Onto BC.
onto BC. So BCD. Oh wait, that would mean BCD infinity would be harmonic, but that's not true, right?
Sorry, I said wrong. BCLW. Yeah, I just
BCLW.
switched L and V.
Oh, okay. Yeah, okay. So BCLW is harmonic. Which would mean BCQ. This point would be harmonic. And it looks like these are also concurrent. So, and that BCA1Q is harmonic. So yeah, we just have a lot of stuff happening. And then G looks like it lies. G looks like it lies on that circle. Don't know, but just I've never seen this kind of diagram before. With you have like the feet of the angle bisectors like this, and you usually connect them. I almost just want to solve the version of the problem without the tangent C, just where we show that Q, L, and S are collinear. Like, to me, that's pretty interesting. So yeah, even if we don't know that G's tangent.
Yeah, I agree. That part is a bit more interesting.
Yeah, do you want to just stick with that for now and hide the rest?
I'm
Or
not sure.
we can leave it for now. We'll leave the rest of the diagram.
What I figured about that part is it is very related to one of the, for me at least, hardest configurations I've seen yet.
Oh, really?
Yeah, the configuration involving circumcircle and excircle.
Hmm.
So like main points of that configuration are not literally points, but stuff about that configuration is taking the common tangents of circumcircle and excircle, and there is this theorem which is pretty hard to prove, that L and T are actually those points on the common tangents.
Okay, so L and T are on the common tangents of the circumcircle and the AX circle.
Yes.
Interesting.
And there is a lot of stuff just going on with the perpendicular bisector of ID, which in this case, it happens to be, I'm not exactly sure why, that actually IX.
Oh, sorry.
It just default to me that D is the tangent point of incircle. Yeah, so in this picture, it happens to be H, to lie on the angle the side bisector, and I'm not sure why. Like, I don't know how to prove it.
Yeah, it does look very familiar, this kind of diagram. So like it looks like H is the antipode of B probably. Oh, so basically showing this is cyclic. If this is the midpoint in this, so yeah, if we knew that it's the midpoints, then yeah, it would prove this bigger one is cyclic.
Yeah, and also a part of that configuration, if you intersected, for example, AH with BC,
yes,
that point would also lie on the external common tangent.
Interesting.
So basically, T and that point would be tangent to the circumcircle.
Or the X circle, the AX circle.
And the circumcircle and the AX circle, yeah. And I know kind of lots of stuff about it, but I don't know how to prove most of them.
Wow.
It's so hard.
That's a good configuration. I feel like someone should make like a packet on it. Yeah.
There is one handout about the configuration, but I think it is incomplete. It has
really?
a lot of stuff, but there are more stuff than in the handout.
Then it's just listed. Interesting. Yeah, you take the perpendicular bisector of IX, you see where it meets the circumcircle, and you connect A to it, and it's like that's on the common tangent, and then T is T where the tangent, like in the more general configuration, is T where the tangent at X prime meets the circumcircle?
No, in the general, T is just T, the intersection of EF with the circle.
Oh, sorry, EF, that's right. That's how we define it.
So you get T and L and two tangents.
Wow, that's really interesting. I'll have to check it out later, see if I can prove it. You know the packet that you said is incomplete, do you know where it is?
Yeah, I can send it.
Okay.
I just need a bit of time to find it.
Yeah, no rush. yeah, it seems like it shouldn't be like, it doesn't seem like it should be that hard to prove that Q, L, and S are collinear. I just, yeah, can't figure it out. All right, let's see. Circum X. Oh, it's opening it up in wow. Rohan Goyal. All right, I'll have to read through it later. Interesting.
Yeah, it has so many stuff, but it's amazing how it isn't complete with all of that.
Yeah. Yeah, EF meets the circle at L and T, TI meets BC at Q, and then we just want to show that Q, L, and S are collinear. Seems like a simple idea, but it's tricky.
Is it possible to use the Zargas theorem for this?
I was thinking maybe the stars at one point.
But yeah, just because SA, LT, and BC, they concur.
SA, LT, and BC. Wow.
That
So,
part is not hard to prove, but
oh yeah, that's just like harmonics. Yeah.
yeah.
So yeah, it's possible. So we want to show SL, TI, and BC concur. And what would be a good triangle? We do like SBC, SLTI, and BC. We did like LBI and STC. I don't think that would work. ISC and LTB. All right. Well, I think I'm going to stop here. I'll look into this later. But yeah, thank you both for staying on the whole time. So yeah, it's a good configuration here. So I'll have to read through that packet. So for everyone watching on YouTube, thanks for watching. If you want to join us in the future, feel free to email me at mgreenby801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day.